Hello, this is Dr. Scott Denstead, founder of EZWxBrief, your best online source for aviation weather and education. Welcome to episode 27 of EZWxChat, a program to discuss various topics related to aviation weather. Well, thanks everyone for joining once again today on EZWxChat. In this episode, we're going to focus a little bit on what I would call weather rules of thumb. And certainly there are many of those out there, and some of them work fairly well, but I want to explain some things so that you better understand when some of these are useful and when they're not. And I'm going to focus on one that really I think is one of the best, and it helps me out, especially when you're flying in and out of airports that don't have a really good forecast in terms of especially wind forecasts. And so we'll look at that later as well. So let's just kind of jump right in. If you're somebody who uses rules of thumb as they relate to weather to do your weather analysis, you might want to think about that again. I see too many pilots attempting to use these rules of thumb sometimes, getting themselves into trouble, because in some cases, especially when Mother Nature is at her worst, you don't want to be in a situation where you are using these rules of thumb and finding out that they don't seem to apply when the weather is at the extremes. And that's generally the case. My other kind of pet peeve with rules of thumb is that they tend to replace real weather analysis. They make the assumption that they always apply. They're always good to apply. And so if you decide, well, gee, I'm going to use this particular rule of thumb and ignore the guidance that's out there that would be better for your analysis, that's again going to be something like an open manhole in a street. You're going to eventually fall into one. So rules of thumb can apply, but be careful about using them, especially when the weather is at the extremes. So a good example of this is trying to calculate the freezing level by using the standard lapse rate. And anyone who's done training with me knows that this is definitely a pet peeve of mine. There are way too many products out there, forecasts, weather guidance, that will give you a much more reasonable estimate of the freezing level, or what I'd like to use the term melting level, than using the standard lapse rate, for instance, to determine the freezing level. The rule of thumb basically says that you take the surface temperature, whatever that happens to be, so you find a particular surface observation. In this case, you look at this surface observation, you look at the temperature showing here is at 38 degrees Fahrenheit, and you basically at that point in time use the standard lapse rate of 2 degrees per 1,000 feet to determine the freezing level. If the lower part of the atmosphere is near standard, it's going to work. In fact, there was a case where the NTSB was investigating an accident due to airframe icing, where a Cessna 172 with a pilot and a CFI on board were landing, I think it was Payne Field up in the state of Washington, and they ended up landing after doing a bunch of instrument approaches. Evidently the landing was pretty hard and damaged the airplane. The pilot was essentially, at that point in time, written up for that particular, I guess the CFI probably was at fault here, but ultimately it produced an FAA enforcement action, and that was eventually bumped up to the NTSB for appeal, and the NTSB agreed with the FAA. But it's interesting, if you read the actual discussion for that particular case, the NTSB even uses the standard lapse rate and says, well, the pilot should have known that given a standard lapse rate, the freezing level should have been at some altitude. And it turns out on that particular day, yeah, that was pretty much standard, but that may not have been the case on any other day. So once again, using the standard lapse rate is not necessarily the best approach here. It would be better to, for instance, use a lapse rate that represents something like, let's go to for instance, a skew-T diagram where you can actually see that here's the temperature at the surface for this particular time. It turns out to be 57 degrees or 13.8 degrees Celsius, and then you can easily look at this and say, okay, now the freezing level at this particular location and time is roughly 11,000, almost 12,000 feet. That may turn out that if you use the standard lapse rate, this may work out pretty well, but not in all cases. When you start looking at different temperature regimes where now it's much colder at this particular time here in Cheyenne, Wyoming, it's 4.9 degrees at the surface, but the actual freezing level is way up there, still at 12,000 feet. So why would you want to use the standard lapse rate here? You're going to calculate a much lower freezing level, because standard lapse rate here is going to put the freezing level just a couple thousand feet above the actual elevation of that airport. But when in reality it's better to use 12,000 feet. That seems to be a lot more warm air near the surface. And it can go the other way as well, because in general most of the lapse rates that we see, especially during the warmer months, tend to be dry adiabatic, tend to be at a point where you can see that the temperature follows this this blue line here, which is the dry adiabatic lapse rate, 3 degrees Celsius. So in effect, it's sometimes if you do that, you may find out you are calculating a freezing level that is actually higher than it really is. It can be dangerous, especially when you're trying to avoid icing. So just don't put yourself into that situation. It's just not a good idea, especially when there's good data information, good guidance out there available for this. But one of the rules of thumb that I kind of like, that I use pretty often, especially at airports that don't have good weather guidance, I will typically use especially for wind gusts, I will use a rule that I'll show you here that allows you to estimate what the maximum wind gusts are likely to be. And so when you are looking at a terminal forecast, for instance, so if I go back to the app here, if I were to look at a terminal forecast, so I'm going to go to the airport view in Easy Weather Brief. I'm going to pull up the airport view here, and I'm going to look at the terminal forecast for Cheyenne, for instance. And it basically says that I've got a wind here of 220, wind direction, 15 gusting to 25. Now, if you're flying out of Cheyenne, you're good to go, because you've got a good forecast for, in this particular case, for wind. But what happens if you're flying out of an airport that doesn't have a TAF or even doesn't have a model output statistics forecast? And there are plenty of them. How do you estimate what the wind gusts might be looking in the future? And the easy solution to that is to use a rule that basically states that at the top of the boundary layer whatever the winds aloft at the top of the boundary layer are, that's the wind speeds that are going to essentially be allowed to mix down to the surface in certain situations. So you basically find the top of that boundary layer, find out what the wind speeds are forecast to be aloft at the top of the boundary layer, and that generally is pretty close to what you'll find in reality to what's happening at the surface. And so let's take a look at that, for instance. So this is out of Cheyenne, and you can see here early in this process here all the way through 0100 Zulu, we have the winds at showing a gusts up to 25 knots. So if we were to actually look at the SKU-T diagram, and you can get winds aloft information in other locations, but I like to use the forecast soundings. You'll see that, let's say at here, let's say at 21Z, you'll notice that we have the temperature at the surface here is 13.8, and the winds are showing around 11 knots, 261 degrees. And so you can pretend that this, for instance, was an airport that did not have a terminal forecast, but we're going to use one just so we can do a comparison. And you'll define the top of the boundary layer. Now, where is the top of the boundary layer? Well, you can see here where the top of the boundary layer is where this temperature is dry adiabatic. So it's essentially following the dry adiabatic lapse rate. And when it starts to turn a little bit to the right, that little bend, this is what we call the top of the mixed layer. And the boundary layer, the top of the boundary layer is just essentially above that. We have something called the entrainment zone right at the top of that, but this whole area, we call this the mixed layer from the surface up to somewhere where that bend happens, and then you get the free atmosphere above that. But it's that wind that's kind of right there at the top of that boundary layer. So if we kind of look at that, that's around 28 knots. You can see that off to the right here, 28 knots. And if you really want to be even a little bit more conservative, you could say, I'll go a little bit higher than that, and the wind speeds are expected to be around 30 knots. And you can look at other times and see the same thing here. Let's say there's 28 knots. This is at 20Z. And the boundary layer here is just starting to take shape. This is at 19Z here. But it's, again, roughly 23, 24 knots in this particular case. So as you are going up in the atmosphere, you can see here, if we change this wind scale, you can see the wind speeds are increasing, which shows you that you've got increasing winds in the boundary layer. And at that point in time, it is these 30, 28 knot winds that can actually mix down. They transfer the momentum. Remember, this wind is horizontal, moving along parallel to the surface, and due to this mixed layer where you get a lot of mixing, that wind at the top of that boundary layer can mix down to the surface and produce those gusts. This really only happens when the wind speeds are essentially in a gusty situation. Also, this particular rule of thumb works well when you have a very well mixed boundary layer. If there was a major inversion, like you see here, that may not be as the case. We still may, in this particular case, have pretty low winds and no little or no gusts here, because of this inversion keeps that mixing from happening. But you can see here we've got this non-convective low-level wind shear going on here, where the winds rapidly increase due to that inversion. It's a topic for another discussion, but the winds rapidly increase from 9 all the way up to around, let's say, 44 knots right in the boundary layer. And you can see that also when we look at here's this, essentially, this is called the non-convective low-level wind shear that you see here. but it's not necessarily a forecast for turbulence necessarily. So we go back and we look at this in the mixed boundary layer. We can take that 30 knots, 28 knots, and assume that's probably going to be the maximum gusts that we're going to see at this particular airport. And if we look and see what's happening right now in terms of the overall observations at this airport, we do see, there you go, 28 knots. So that's pretty close to what we're looking at here. And it's gotten as high as 31 knots. So once again, you can go up a little bit higher with that to be a little more conservative. But essentially, you're dealing with wind speeds that are in the 30 knot range in terms of gusts. And you can see even before that, the winds are pretty light. It's not until that boundary layer gets established, you get really good mixing in that boundary layer happening, and then it can mix down that particular strong winds aloft down to the surface. And you'll notice that as the day wears into night, those winds eventually stop becoming gusty once the sun sets. And roughly because of the fact that you're not getting that mixing, that low-level inversion is starting to kind of take shape here. So we'll see that as we go through this. You see that well-mixed boundary layer here that's very unstable eventually starts to develop into that kind of surface-based inversion, and then you can see how that surface-based inversion eventually develops and becomes very stable atmosphere near the surface all through the night. And as that happens, you'll notice that the winds here, let's say between 5 and 10,000 feet, watch what happens to the winds there. As I walk through that, the winds start to really increase near the surface. See, now we've got a really strong wind, and that's all due to this stability that's taking place, decoupling the atmosphere, basically decoupling the atmosphere from the surface friction, and that allows that air to freely accelerate right above the surface. So 9 knots at the surface, and you go up 1,000 feet, 2,000 feet, and you find yourself with winds that are looking at 48, 50 knots, and that's that non-convective low-level wind shear. And you can see on the terminal forecast that they only forecast that really between 1Z and 3Z. So it's really not even that many, it's a couple of hours of time, but in reality, it's actually going to last all the way through until well into the next morning. So it's not even forecast beyond that. Again, it seems kind of strange that that's the case, but for this particular forecast, they don't even show it beyond that. And it turns out that it actually could be a little higher than this as you get into the overnight hours. And we're finding that, again, this is not a forecast for turbulence, but overall, due to that stability, these winds don't mix down to the surface and therefore should not produce any strong wind gusts. Although it says here after 3Z, it's a possibility of winds gusting to 28. It'd be interesting to see if that really happens. That seems to be, in this particular situation, that seems to be at 3Z and beyond, not very likely of a situation, but it certainly could be, but it would be interesting to see how that all turns out. For the most part, though, getting back to that wind gust estimate, this is, again, one of my favorite go-tos, especially at airports that don't have a wind forecast. I can quickly look at this and determine, based on this, what the maximum wind gust will likely be, again, at the top of that boundary layer. If there's not a really good, well-defined boundary layer, likely the winds are not going to be strong and gusty below that, unless there's something else going on here in terms of the overall weather impact for this. And so you might find that this would be useful. In many cases, I would not necessarily, let's say I would not use this as a rule of thumb. Even if there's a TAF there, I would still look at the terminal forecast, still look at the model output statistics forecast to see what the actual winds are. And we can see here, if we go back to the map, and we look at the actual EZWxBrief forecast for Cheyenne. That'll also be another way you could utilize. We have a fairly large number of airports from a wind gust perspective, so you can actually then see, let me turn for the wind layer here. We'll turn on just the wind gusts here, and we'll see what happens out of this. So this is another way to kind of look at it from that perspective. So this again shows that there could be some gusty winds, and this is actually showing that, yes, even beyond that period of time, this is showing the possibility of gusty winds even into the overnight hours here in Cheyenne. So there are really good ways to determine airports, especially larger airports, what the wind gusts might be. So you definitely don't want to ignore those. But if you happen to be flying out of an airport that doesn't have one of these, take and try to use that particular rule of thumb to estimate what the kind of the maximum wind gust would be for that particular location. Well, that wraps up episode 27 of Easy Weather Chat. My name is Dr. Scott Denstead, and as always, I hope you enjoy the simplicity of EZWxBrief.